Hi, I'm James Rapley, and I want to talk about antimicrobials and how they are a key pillar for sustainable coatings. All right, so we'll skip the bio here. So let's dive right in. So we'll talk about what the mission is and what goes into creating sustainable coatings. Then we'll look at the microbial attack that occurs onto the coatings. Then we'll talk about the solution and how we can combat that microbial growth using antimicrobial coatings. Then lastly, we'll look at some of the novel antimicrobial technologies and what they need to do in order to remain in step with sustainability efforts. All right, so first looking at the mission. So here we have outlined a couple of factors that go into creating sustainable coatings. And what antimicrobial technologies need to do is make sure they are in alignment with all of these efforts and consider them as much as possible. So again, when we talk about reducing toxicity, we have to make sure that we're picking materials that have a better toxicology profile, better ecological profile, and it doesn't impact the environment and is safer for people to use. Looking at improving stability. So again, we don't want to introduce antimicrobials additives that can inadvertently destabilize a system, and so maybe decreasing the pot life or maybe the shelf life of the antimicrobial itself is very short, and so that can increase waste if you have unused material that you can't actually incorporate. Looking at improving process efficiencies. So again, as efforts are being done to make sure that the process can go faster or mix times are reduced or overall energy expenditure is lessened. Again, introducing antimicrobials, we don't want to go against those efforts. Specifically for solvent-based systems, again, looking at reducing VOC emissions. So a lot of effort goes into reducing VOC content. We don't want to introduce antimicrobials that can actually contribute to those VOC contents. Looking at reducing waste generation, again, making sure that when we add the antimicrobial additive, we aren't certainly creating other defects or things that could cause for scrap rates to increase or impact yield negatively. And then lastly, looking at the overall extension of the product lifetime, again, make sure that the product remains as new as possible for as long as possible and maintains the performance properties that we expect. Right. So looking at this a little bit more closely, it's well understood exactly what we protect our coatings from in order to increase the coating product life. And a lot of these are things that are just ubiquitous to a coating formulation. So when we talk about UV protection, again, introducing UV stabilizers. That way, if the coating is exposed to UV light over time, we don't want any sort of free radicals to start to create, and that can start to destabilize the integrity of the polymer. So you introduce those UV stabilizers in order to quench that reaction and prevent that from happening. We talk about slip and abrasion resistance. So again, mitigating any sort of mechanical forces that can inadvertently impact the coating, create scratches, create scrapes, or create flakes that can come off. So you may introduce some inorganic fillers there to make sure that the coating is actually resistant against those type of external forces. Looking again at chemical and stain resistance. So if you can imagine, you have a new table. If you spill coffee on it, you don't want to suddenly have to throw the table away. Or a new carpet, you don't want to spill juice on it and suddenly you have to get rid of that carpet because you have this stain sitting there. So the more chemical resistant the material is, it extends the overall product life. And then looking at adhesion improvements, again, if you think about like car paint, for example, the efforts that go into pre-treating the surface of the metal prior to adding any sort of coating, or adhesion promoters that can go directly into the formulation, with the entire goal being to make sure that the coating adheres for as long as possible. And then we want to go back and look at antimicrobial protection. And we think this fits in perfectly with all of these components because microbes are ever present, and so making sure that the coating is protected from them is just as important as making sure that those coatings are protected from UV, or those coatings are protected from any sort of external forces that can occur. Right. So now looking at the microbial attack. So there are different types of microorganisms, but we want to classify them into three main categories because this is what we typically see affect the coatings world. So looking at bacteria, mold, and algae, again, these can exist in different places depending on the end use of the product. But generally speaking, these are the things that we screen for. And here we have a real world example of a soap dispenser. And if you look at this soap dispenser, it's probably something in a random bathroom somewhere. But you can see under the lid, you can start to see how resilient these microorganisms are. And you can see the buildup starting to happen. So if you're a manufacturer of this material, you're able to, you see clearly what the problem is, and you have an opportunity to really differentiate. And so antimicrobial coatings are able to take this type of problem, and if applied properly, it's able to mitigate that type of growth and prevent this from causing any further issues. Right. So looking more into microbial attack and how it works and what happens. So in general, we're looking at a very simple situation where you have microbes that exist everywhere and they exist on the surface of a given product. And you introduce some organic matter. This can be oil from skin, oil from fingertips, anything like that. And that's what the microbes feed on. And then those microbes go through a metabolic pathway that creates these metabolic byproducts. And it's actually the metabolic byproducts that impact the coating. So, for example, when we talk about cracking and brittleness, some of these metabolic byproducts can be acidic. And so if they're acidic or they're alkaline, if they create an environment that can start to eat away at the polymer, that's where you start to see issues with the overall integrity of the material. Also, if the polymer is scratched or something like that, the microbes can then get into those cracks and they can start to populate there, and they can start to go and impact your adhesion. Whereas if you have an antimicrobial, you can mitigate that process. Looking at discoloration and staining, again, like the example that we saw earlier, as that population starts to increase, you start to visibly see it, and it starts to have a negative effect on the overall product. And then lastly, looking at odor, again, all of these kind of tie in, and all of these can happen simultaneously. But essentially, if you've ever opened something and it has that mildewy smell or maybe a sulfuric smell, that's due to the microbial growth is happening. And so antimicrobials can prevent all of that from happening, and we prevent it from happening on the dry film as well. So looking at the solution and talking about antimicrobial coatings. So here we have a simple diagram to sort of explain exactly how they work and how they're incorporated. So first, you apply the technology. The technology, if it's a good technology and it's been selected properly, it'll go into the system during the mixing process, and it should not impact any of the mixing. That's the overall goal. And once it's mixed and the coating is then applied and dried, then you have the antimicrobial embedded into the polymer itself. And that's where you have your protection. And so as these microbes begin to grow and they begin to populate the surface, the antimicrobials that are present actually prevent the microbes from undergoing their typical metabolic pathway. And because they're not able to go through that process, they're not able to propagate and continue to replicate on the surface. And that leads to the cleaner products the cleaner products that we talk about that have the reduced microbial population existing. And so then you mitigate those issues that we talked about earlier in terms of odor, brittleness, discoloration, staining, anything like that. So one key question is, do certain coatings already have some type of antimicrobial properties? And the simple answer is yes and no, and it really depends to varying degrees. So what we wanted to do was try to demonstrate how this works and what we've seen in the lab here. So what we did was, one key thing that you can kind of think about from a formulation perspective is what happens if we tweak the surface energy and modify it. So we can create hydrophobic coatings with the thought being, if I repel the carrier, which in this case will be water, then I prevent the microbes from even being able to stick onto the surface. If they can't stick onto the surface, then we don't have to deal with some of those negative problems that we talked about before. So what we did was control for the hydrophobicity by creating a coating that had a contact angle of 110 degrees. So a pretty good water repellency. And with that, we compared the untreated hydrophobic coating to a treated hydrophobic coating. And what we saw was the untreated hydrophobic coating was still susceptible to microbial growth. So what we have here on the chart is looking at the log reduction. So a lower log reduction means higher susceptibility to microbial growth. So lower logs means the microbes are able to grow and populate the surface more, whereas higher log reduction means that the population remains low. So here we actually were able to achieve what we would consider excellent um, uh, uh, antimicrobial properties by reaching 4 log reduction here. Right. So then looking at kind of another general question that we get asked very often is, what about solvent-based coatings? Because as we know, in terms of in-can preservation, only water-based systems really need to consider that, because the water can actually support algae growth and mildew growth, and so it's very common for water-based formulations to just have antimicrobials present in order to prevent that from happening during the shelf life of the coating of the formulation. But on the solvent-based side, that's not the case. However, what we saw was, once you take a solvent-based coating system and you apply it and you remove the solvent once it's dry, you actually end up with the same situation where you have an unprotected dry film that then needs antimicrobial technology in order to preserve it from microbial attack. And so here we have a clear example where we have an untreated solvent-based coating and a treated solvent-based coating. And the untreated solvent base has a reduction of less than 90%. And so again, that's not a strong performance there. So it has some, but it's not strong enough performance to where what we tend to target. Whereas we look at solvent-based coating that's been treated, again, you then hit that 99.9% reduction, 0.99% reduction there. And another key thing that we want to point out is, even if a coating does have some type of antimicrobial inherently, antimicrobial behavior inherently, it does not qualify to be able to make any sort of customer-facing antimicrobial claims, which essentially is just another benefit of having the antimicrobials present, because the technology can then be communicated to the end user that is present and that is actually extending the product life as well. Right. So now looking at dry film versus in-can preservation. I talked about this a little bit earlier, but in water-based systems, we definitely understand in-can preservatives, being able to add antimicrobials in order to make sure that there's no mildew or fungus growing inside of the material as it sits in a shelf, or maybe if you're manufacturing, it may be sitting in a huge vat or a container, so you don't want to open it and have that strong smell hit you. But when you compare that to dry film preservation, typically the in-can preservatives have a minimal amount of additive, and that minimal amount does not carry over to the dry film preservation. And so it does not extend to the dry film. And so then once the film is dry, now again, you're exposed to microbial attack. Also, with the antimicrobials present in the dry film, now you actually are extending the finished product lifetime, whereas in can preservatives, they're not designed to do that. That was not their intent. And then lastly, with dry film preservation, again, we talked about being able to make those treated article claims, being able to communicate with your customer that the technology is present and that the technology is actually protecting the end product. And that's something that you cannot do with in-can preservatives. Right. So now let's look at some technologies specifically. So we sort of delineate between water-based and solvent-based coatings because there are some considerations for one that may not exist for other. So there's some overlap, but also we sort of pick our treatments based on whether it's a water-based system or a solvent-based system. Again, to try to be in alignment with the system and make sure that we're as compatible as possible. Right. So look at some of the challenges that traditional antimicrobials face. Essentially, instead of just looking at efficacy and being concerned with only making sure that we have antimicrobial protection, traditional antimicrobials also now have to consider a multitude of things throughout the entirety of the process. So with water-based systems, because you have the presence of emulsifiers and dispersing agents, and you have to consider pH and ionic charge, those antimicrobials really need to make sure that they're compatible. And oftentimes that can be a challenging feat. Also looking at the mixing that we talked about earlier. So if you have a antimicrobial that does not go in easily, it can impact the mixing times. Mixing may need to be increased. More energy may need to be put into it in order to get it to integrate properly. So again, going against the sustainability efforts. These things can be prone to clumping, and they can lead to non-uniformity, clouding, and speckling of the final coating. So again, now you start to impact the yield, and you start to increase waste. And then also, a lot of times these antimicrobials may be hygroscopic, and so the shelf life of them, as soon as they're open, you may not be able to close them again or reuse them for another run. And so again, you increase waste because you can't use the material over and over again. So we wanted to try to demonstrate exactly how this impacts the coating. So in the bottom right here, we have a graph, a chart that looks at a compatible antimicrobial versus an incompatible antimicrobial and how it impacts the defects. And when we talk about compatible versus incompatible, what we're looking at is two antimicrobials that go into the solution well. However, one we know over time starts to aggregate and form sedimentation, while the other one doesn't. And what we saw is over time, as you start to see an increase in defects. So we took the film and we actually did a drawdown, and we then analyzed the film using an optical microscope. And then we used the auto count software to sort of place and parse the size and the amount of defects that we saw. And what we saw was with incompatible antimicrobials, you start to see much larger chunks. And those larger chunks can lead to what we would consider defects, or depending on the specs, you may start to see things that don't necessarily pass your internal specs, leading to higher scrap rates, lower yields, and again, we go back to going against sustainability. Right? And so with key innovations for water-based coatings, again, one other thing to consider is moving away from heavy metal-based materials and moving more towards heavy metal-free solutions that are more stable in water-based systems. So again, the goal is eliminating the struggles associated with aggregation and sedimentation. So making sure that it goes in seamlessly and it integrates for a much longer time, so improving the shelf life while still maintaining bacterial efficacy. Again, another key consideration is being ideal for optimal clarity and thin coatings. So this is a fairly new development when we talk about having antimicrobials that not only work, but they also don't impact color. They also are optically clear, and they can go into thin coating. So if you think of a coating that's less than 5 microns, and this becomes important because as antimicrobials find more nuanced applications, and it's not just in places that maybe people don't see, you may have a glass or a piece of polycarbonate that needs to remain clear, but you want to add a coating on there that's protected by antimicrobials. And so we'll see some examples of that where if it does create cloudiness, that can be a problem. So looking at this image at the top, we just have a clear example of, on the left, you have something that just remains clear, even though an antimicrobial is incorporated. And then you can compare that to some of the more cloudy solutions that we have here that can start to settle. And again, as we talked about, once dry, it can start to create cloudiness or speckling. So again, looking at the optical clarity here for a second, again, new antimicrobials trying to make sure that they remain optically clear in any type of top coat actually becomes much more important. And we see here, if you compare more novel antimicrobial technology to sort of a more traditional standard dispersion, you can see the dispersion starts to have that cloudiness. And it may not be a problem depending on the color and those type of things. But again, as the antimicrobials become more ubiquitous, you want them to be as compatible with as many systems as possible, including clear coating systems. Right. So next, looking at performance data. So we took our antimicrobials and we want them to be compatible with as many chemistries as possible. So here we have a comparison of acrylic coatings and polyurethane coatings as just two main classes. And again, if you look at the antibacterial performance, larger numbers are better. So 99.9% reduction is good, and 99.99% is even better. So that means the population is as low as possible. And then looking at a antifungal test, again, we're able to pass antifungal tests as well. So we're still getting good antimicrobial protection. And lastly, just comparing a treated versus an untreated system. Again, I talked earlier, depending on the system, depending on the formulation, there may be efficacy that exists within the coating. But what we typically see is it does not last. So over time, through off-gassing or through exposure to the environment, you actually start to see the inherent efficacy start to go away. And so we can see when you add treatment, you actually get that strong antifungal and antibacterial performance, and that performance stays with the product, with the coating. And here we just have some suitable applications. Again, just some examples of just the wide range of different applications that we see now, because antimicrobial and microbes are much more prevalent in terms of the consumer and what they're looking for. Right. Then some key features. So just running through and again saying something that's using things that are easy to use during manufacturing, heavy metal free, make sure that it still performs properly, so it has a broad spectrum performance, and then has improved shelf life and UV stability. All right, so now looking more specifically at solvent-based systems. So again, there's a lot of overlap. So you'll see that we still want to maintain clarity. We still want to be easy to incorporate, mix, and disperse, and be stable for a long time, right? So that still maintains it. That's still true. So we can compare that to, again, a more traditional antimicrobial, and you start to see the cloudiness and you start to see the settling. So we want to move away from that, but we also still want to maintain bacterial performance and antibacterial performance. And so we still have that 99.99% reduction. And that's always the target, as well as making sure that we're UV stable and ideal for thin and transparent coating. So again, going on to thin coatings and being able to maintain transparency. So here we have examples. When we talk about looking towards nature, this is something that we're excited about as a whole when we talk about the industry and new technologies and chemistries that are surfacing. And so we have, for example, lignin is a great example that you've probably seen a lot in terms of development efforts. This is a non-petrol-based material that can be used to create resins and binders that would actually serve as the foundation of a coating formulation. And these are naturally occurring in plants and wood and bark. Chitin is another example, again, being used to create films. This is something that occurs naturally in the hard shells of crustaceans. Alginate is actually another thing that's being used to create fibers for wounds and those type of applications. This is found in seaweed. And then lastly, we're looking at phenylpropanoids. So again, something that's naturally occurring in plants, and this can be commonly used as food preservatives. Right, so here we have a comparison. Again, going into the inspired by nature technologies, not all of them will work for all applications. So a lot of work and development has to go into choosing the right ones and choosing the right application. So here we have just a comparison of two different phenylpropanoids. And again, you can see one performs pretty well on the left. It's okay. It's not so good for E. coli. Whereas when you find the right one, it actually performs well for multiple organisms, and it can give you great antibacterial performance. And it still is clear. It still has superior shelf life stability. It still has UV stability. And on the plus side, it's also inspired by nature. So again, trying to mitigate that impact on the environment. So here are just some examples of some real world products that are using this type of technology. So we can see paints here that are on top of a polycarbonate polymer. Again, the paint goes on aesthetically. You don't know that the antimicrobial is present. And a very good example is that UV clear coat glass here on the right side. That coating is aesthetically clear, and you don't even know that the material is there. And that's, again, one of those inspired by nature technologies that's looking towards more greener solutions. Right, and then key features, again, nature inspired, something that's compatible, again, moving away from heavy metals, very easy to use, going into systems without much mixing, and UV stable, and giving the overall improved quality. So lastly, looking at encompassing everything that we talked about, it's all cyclical. It's all cyclical. So you start off with what type of antimicrobial you choose. And I'd say just ask it up front. Do you have any non-heavy metal solutions? Do you have any solutions that are inspired by nature? And then those same solutions also need to be sustainable from a manufacturing standpoint. So they need to make sure that they're not contributing to waste, not contributing to scrap, not contributing to increased mix times, etc. Then looking at the consumer experience. So again, the goal is to extend the product life so the consumer receives a product that meets their standard. But there's an opportunity there for product differentiation. So again, you can actually take these antimicrobials, incorporate them, and you can let your customers know about it and let them know how the technology is there and is helping their product. And then lastly, being able to mitigate the environmental impact. So again, that first choice of antimicrobial you have circles all the way back to making sure that we mitigate the environmental impact. All right, so thank you for your time and your attention. My name is James Rapley, and I look forward to any questions that you have. Thank you.